Good. Last time we started our discussion about nonlinear systems, not involving or not including for the time being the notion of control, because we need to analyze the notion of nonlinear systems and to understand the basic concepts of mathematical analysis of such systems, okay, and system theoretic analysis of such systems, as it were. Hence, first of all, we discussed last time some essentially nonlinear phenomena. These are peculiar to nonlinear systems and typical to nonlinear systems and atypical for instance, for linear systems. So these are new things that you have never encountered before, such as the finite escape time, which is something typical to nonlinear systems, okay? The existence of the discontinuity of the solution, even if the model itself is continuous, okay? Secondly, it's about the multiple isolated equilibrium points, okay? So this is just like the pendulum. This is not possible for linear systems, okay? And then there's limit cycles, okay? And there's limit cycles, limit cycles, again, these are structurally stable, and we are going to understand this notion of structurally stable sometime soon. Oscillations, okay, so they, even if they are perturbed or even if they are so subject to any perturbation, okay, or subject to any problems, these oscillations are maintained forever, okay? And of course, chaos, that is a set of differential equations behaving like with a chaotic behavior, even if they are completely deterministic. And the example we gave here is the Lorentz model, okay, implemented in MATLAB, governed by by three differential equations with mild polynomial nonlinearities. Mild polynomial nonlinearities. And if you remember last time, and I asked you to do this in MATLAB, if you run Lorentz, you saw what happens, okay? Right, so let's dive a little bit deeper into the details of nonlinear control systems, and we are going to talk a little bit about what mathematical modeling is, okay? I'm sure that most of you or all of you have followed have followed courses on modeling and simulation before, okay? Have taken such courses, okay? And there, of course, there was the industrial discussion, if you like, about mathematical modeling. Whereas here we are going to emphasize the idea of mathematical modeling in the sense of systemic properties and of systems theory. We have to understand what a mathematical model is from a mathematical and physical point of view, and what a mathematical model is from a systemic point of view. So what's mathematical modeling, essentially? Writing equations describing relations between different variables. This is rather, I wouldn't say obsolete definition, but maybe not complete. Why? Because nowadays there is data-driven modeling. You must probably, I'm sure you must have heard this term recently about data-driven modeling. That is, you compare sets of data, input and output sets of data. You separate them into input sets of data, output sets of data, and then you try to interpolate such data, okay, to a specific model. So essentially, the interpolation problem is you have a set of data. Let's use the matrix vector notation. Okay, so you have x1, x2, x, I would say n, and so on, input data. Okay, and you measure the effect of such data upon your plant. Okay, let's call it a plant at this time, and you have output sets y1, y2, and yn. Interpolation, okay, interpolation means find f, okay, find f, some function, some operator, such that capital F, such that f xi is yi. This is essentially, very briefly, the definition of interpolation. And based on this, you can easily compute, or not easily, there's algorithms to compute mathematical models based on such an approach. Okay. However, for the time being, we restrict ourselves to Newtonian, Newtonian-based modeling, in the sense of writing conservation laws and motion laws, okay, and from these laws to gather the differential equations, okay, emphasizing the dynamics of the system, okay. So this interpolation thing is data-driven modeling nowadays, which is a bit more than what is written here, system identification, okay. So system identification plus interpolation of large data sets, because you have large data sets nowadays. Data sets results in data-driven modeling, okay? So this is the big area nowadays, talking about issuing or rendering mathematical models from only from sets of data. Okay, so again, we are going to use a lot this Newtonian approach. So when elaborating a model, one has to do a trade-off. So there is a trade-off between the complexity of the model and its accuracy, and we're going to see a couple of examples about that. Okay, the simpler and the reduced number of equations the model has, the more coarse, I would say, the effect of the model is, coarse in the sense of the approach between what the model issues and what the real simulations or the real outputs are. Okay, so of course, accurate models contain more variables, contain more equations, and of course, I would say include more nonlinearities than we can handle. Let's put it this way, or more nonlinearities than the machine can handle. Okay. So what is a good model? This is the question. The good models is when the differences between the experimental results and the calculated results, the computed results, are smaller than some prescribed tolerance. Okay, this is when a model is called good. On the other hand, if you have complex model, there is a field called model reduction. For instance, Andrei followed this course last semester with myself because that's my research subject. Okay, and there is a whole area studying the possibility of approximating complex and large scale or largely dimensional models with smaller, simpler models to capture the main input-output behavior. But that's a different story, and that's a different course. And I did that last semester. Okay. Nonlinear dynamical systems. What are they? Appropriate models. They are more accurate than their linear counterparts. That only makes sense. That's the reason why we study nonlinear systems and implicitly nonlinear control systems, because the more realistic the model is, the better understanding of the phenomenon we get, or the plant we get. Okay. Of course, we have methods and concepts tailored to the engineering practice. We try to do this in the nonlinear setting as well. I mean, of course, the nonlinear setting is more mathematized, I would say, than the linear setting, although in the linear setting as well, there is a lot of mathematics involved, a real lot of mathematics involved. Okay. Yeah, we are trying to do this to bring this engineering approach to the nonlinear systems as well, and to nonlinear control systems in particular. There's also nowadays a lot of revolutionary applications, such as mathematical modeling of genetic circuitry. Okay, so a lot of this modeling and these tools have penetrated the field of biological systems, okay, in genetics, in enzyme processing, and so on and so forth, okay. And it's a big field, and my colleague, Professor Radu Ștefani, is working quite a lot in this area. We are going to present ourselves a little bit of biological stuff in this respect. Okay, you remember the history of all this? I told you last time the history of the things and how things got to this nonlinear stuff, and now we are going to get into the mathematics of it. Okay, so we are going to talk about mathematical models. We consider a system, a general differential system, x dot t is f of t, x, and u. So it's a vector field, okay, depending on the time, on the state x itself, and on the input u, and the output y, which is a, so the first equation is a differential equation, the second ordinary differential equation. Let me make this, note that this is an ordinary differential equation. And the second equation, which is an algebraic equation, okay? Y is GTXU, where f is defined on some domain included in the domain Rn plus 1, so R times Rn. It's written like this to emphasize the explicit dependency on time, Rn from the state and Rm from the one of them is M, sorry. This should be M. One of them, it depends on the input is the space of the input U, valued, so it's in Rn, yeah, okay. And G is another function which is continuous, and X, U, and T, X, U, and Y are the state, the control, or the input, and the output of the system, the measured output of the system, I would say. In general, the models that we are familiar with make this assumption that the functions f and g do not explicitly depend on time. They are time invariant. Okay, so I would say not necessarily for the sake of simplicity, but it is for the sake of actually a bit of it is for the sake of simplicity, but for the rest of it is not restrictive. So there is no loss of generality taking into account this assumption of time invariance. Okay, and you can easily write the system 1 as number 2, considering that you have a control input. So this is control. What is actually this telling you? So if you have this is your system sigma, governed by x dot is f x. Oh, sorry. Let me rewrite this. Let me make it larger. So you have the system, x dot is f, x, and u. This is the output y. And if you put here a control signal, gamma x, okay, and you take u to be gamma x, okay, actually this line shouldn't be taken from here. This line should be taken from here, okay, gamma x, because here you have the state x, and this is g of x and u, okay, and this is u, okay. So this system, okay, it's an autonomous system. This is an autonomous system. X dot is f of x. Okay, x dot is f of x. That is, this is a state feedback control. Okay, so gamma can be considered a state feedback control, and this is customary in multivariable control systems. Okay, you did this for linear systems with ABCD as well. And you can consider, we are actually going to look a lot at equation number 2 with the initial condition x naught. Okay, we make the assumption that all the functions in f1 up to fn, they're continuously differentiable. Actually, we can consider them smooth. And such a vector of differential and continuous functions and continuously differentiable functions is called a vector field. It's called a vector field. So, a differentiable function phi defined on some domain such that phi of t0 is x naught and the time derivative of phi is f of phi t is called a solution. It's called a solution of the so-called Cauchy problem. The Cauchy problem is the problem of finding a solution of the differential equation under specific initial conditions on the interval I, which is a subset of R. The image of the solution phi in the domain D subset of Rn is called the trajectory or the orbit of system 2, and it's a parametrized curve in time. Okay, it's a parametrized curve in time. So essentially, it says here, so if you remember last time we discussed, if you have x dot is ax, this is linear, which with a real constant, and the initial condition x naught. You remember that x, the solution x, is e to the power at times as x0. So this is actually phi t. And we see that phi dot t is x naught e to the power at. We take the derivative dot. So this is a x dot e to the power at. But this is actually phi. So indeed, it is, okay, you can call this fx. Okay, so this is indeed f of phi t. So this is the solution, yeah, phi t, which is explicitly written like this, okay, is the solution of the system. This is how you define the solution of a dynamical system mathematically. And it makes sense. Of course, mathematically, the solution is phi, but systemically, the solution is this orbit, is this the trajectory described by the function phi, okay? Okay, so the trajectory passing through x naught at time t naught is denoted by phi of t naught x naught, or phi of t x naught when t0 equals 0. So this is how you define the trajectory. This is the trajectory defined by the solution phi t. So you see there is a one-to-one relation between trajectory and solution. Okay, how is the vector field f with respect to the solution phi? Of course, it is tangent because it's a derivative. Okay, it's tangent because it is a derivative. Sorry. So that the vector field f is tangent to the trajectory phi t x naught in the point x. Okay, and this is a state space. Figure 1 shows you a state space. Shows you a state space trajectory. Okay, you can see the vector field tangent. The second important definition for a nonlinear system is the equilibrium point of a nonlinear system. And the equilibrium point of the system x naught is fx is a point x star satisfying the following properties. X t naught is x star, implies or leads to x t naught is x star for all t larger than t naught. Okay, so an equilibrium point is that point that has a constant trajectory parallel to the horizontal axis, okay, with a constant value for all time t. This is called equilibrium point. This is called an equilibrium point. We call x star an isolated equilibrium point if there is a neighborhood which contains no other equilibrium points of such a system. Okay, so any equilibrium point is a singular point of the vector field f. So essentially it's the solution of the equation f x star is equals 0. So phi of t and x star is a constant or trivial solution of the system. So it's still a solution of the system, is the trivial one. It's funny that we're actually looking for the solutions to be trivial. This is our desire: trivial, simple, constant solutions, equilibrium points. Okay, we'd like to do that. Of course, we'd like to have them stable. So we'd like the system to when subject to perturbations, to always be able to return itself to the equilibrium point. We have examples. For instance, the first example, x dot is sine x. We solved this last time. So the solution sine x, I remind you, sine x equal to 0. This equation, okay, this is the sine, has the solution k pi with any integer k. Okay, so they're all isolated because there is no other one. Okay, so it's 0, pi, 2 pi, 3 pi. So there is a neighborhood, quite large, I would say, where you cannot find any other equilibrium point. B, the second one. So the second one is x1 dot is x2 plus 1, x2 dot is 1 minus x2 squared x1. Okay, so here we solve the equations. X2 plus 1 equals 0. 1 minus x2 squared x1 equals 0. So then from this equation we get x2 equal minus 1. And from the second equation we get 0 x1 equal to 0. So that means that x1 star, here I should put star, x1 star is any real number alpha. Okay? So the equilibrium points here are of the type alpha minus 1 with alpha a real constant, and none of them is isolated, because no matter how small a neighborhood you pick, you always have another equilibrium point around in this neighborhood of your prescribed equilibrium point. So this is not isolated. So you see, nonlinear systems can have non-isolated equilibrium points. Okay. All right. Here you have x dot is 2 square root x, and the initial condition is x naught equal to 0. So you have the trivial solution phi t0 equals to 0. This is not unique. So you do not have only the trivial solution. You have to find a non-trivial solution. And how do you do that? So you need to solve the differential equation. Solve the differential, equation, yeah? So we have, once again, x dot is 2 square root x. So let's use the separation of variables. So you take everything with x, you put it to the left. So you have 1 over square root x dx equals 2 dt. Okay, just like that. Okay, this is the separation of variables. You separate the x variable from the t variable. Okay, and then you take the integration. Okay, on the left you integrate from x naught to x, and on the right you integrate from 0 to t. Agree? So this is x to the power 1 over 2 between x naught and x. Agreed? It's agreed. Yeah. Okay. Equals to t. right? If you see a mistake, please let me know. Okay? So then you get square root x minus square root x naught equals 2t. Then you get square root of x is 2t plus square root x naught. True? So then you get x equals, so the solution x is 2t plus square root x naught square. Oh, it's 0, so the initial condition is 0. X naught is 0, so the solution is x of t is 4t squared. Agreed? Correct or not? I think it's correct.
Teacher?
Yes.
I think the integral of 1 over square root of x is 2 square root of x.
Oh, yeah, should be 2. Right. Then you just do this. Okay? Because the 2 goes away, right?
Yes.
Is that what you're saying? Okay. Then it's this. Okay? Yeah? So look, yeah, indeed. So we have the non-trivial solution, x of t equal t squared, which is non-trivial. Right. Then you get x dot is minus x squared. X0 is minus 1. This is interesting. So x dot is minus x squared. Again, separation, because there is no other tool. Separation of variables. We do this again. So we get minus 1 over x squared dx equals y minus. I shouldn't use this minus here, so I can keep the minus on the other side, right? Minus dt. Agree? So you take the initial condition, then you get what? What is the integral of x, x minus 2? So this is what? It's like this, right? True? Huh? Sorry, minus t. Agreed? I think this is correct, right?
Yes.
Yeah. Then you get that minus 1 over x minus 1 plus 1 over x0. Oh, but the minus goes away, sorry. The minus goes away. So it's 1 over x minus 1 over x naught equals t. So that means that 1 over x is t plus 1 over x naught. Then this means that x is 1 over t plus 1 over x naught. True? True? Okay, so for instance, if x naught is negative, okay, then what can we notice? We notice that limit when t goes to 1 over x naught from x of t goes to what? So how much is this limit? How much is this limit?
X0 over 2.
My friend, when t goes to 1 over x0, and x0 is negative, or minus 1 over x0, sorry. Sorry, minus 1 over x0. Right?
Yeah.
Infinity, so finite escape time, nonlinear phenomenon, finite escape time, you see? So here they gave x not equal minus 1. So look at this solution, t equal to 1, finite escape time. So the domain of definition of the function phi is the whole real axis less without the point 1. Yeah, this is finite. Yeah, so the answer to this question is yes, finite escape time. Okay. Again, then this one, double y is 1. So this can be easily integrated. So you can make this a system. Okay. So you can have this such as x1 dot is x2, x2 dot is 1. Okay. x2 dot is 1. So you can try to solve this guy, okay, or you can just easily integrate this, and you just use separation of variables twice, and try to find a trajectory using these two, because you need now 2 points. You need 2 initial conditions, y naught and y dot naught. Do you agree? So essentially, y dot t is t, right? Should be t, true? T minus the initial condition y dot 0, right? It's like this, and then you integrate once again, and you can find this. Of course, you need both initial conditions. Okay, right. So we are going now to look at some specific examples of the pendulum, the neuron, and I might show you some other examples as well. Okay, let's have a short break and let's meet in a few minutes. Agreed?
Yes, it's fine.
Okay, fine. See you in a couple of minutes. Right. So where were we? Cool. Right, the pendulum, yeah. So essentially, you can see this is the figure emphasizing the pendulum. So what is a pendulum? Is a rod of length L pinned to some wall or something, or hanging from something, and swinging back and forth. It can swing forcefully, or it can be moved forcefully using um, TC, the force TC, okay, and then, or it can be left to swing. It can be left to swing and subject to perturbations, and then we can see what happens. So we just look at the physics of such a system and write the movement laws. Okay, so this is what, note that these are not forces. Okay, these are torques. Okay, so this is the movement torque. This is this is the inertia, I equals ml squared. This is the inertia of the pendulum. Okay, so ml squared theta dot. Note that this is rotation motion laws. Okay, this is rotation motion laws. So the equilibrium of forces. Okay, so movement torque mt, let's call, or tm, let's call it, the torque of the movement, plus the torque of the gravity, a component of the torque of the gravity, because look at the gravity. So what you do, you decompose the gravity force into the tangential gravity and normal gravity. Okay, so this is gt from g tangential. So this is the torque of the tangential gravity, because the normal gravity has no influence whatsoever on the motion of the pendulum. Okay, so this is the gt torque plus the torque given by the friction force. Okay, the torque of the friction force minus the external torque. Okay, this should be 0. So this is the second, this is a conservation, a second motion law from the Newtonian point of view of the rotation motion of such a pendulum. Okay, so it says here, but so theta is the angular position of the rod, theta t is the angular position, and then you have theta t dot is the angular speed or velocity, The rod is rigid and has length L and is assumed to be of null mass. So we use Newton's second law of motion applied to the bob of mass m. Okay, and then you just substitute for each of these torques its formula. This is the inertia times the acceleration. Yeah, so theta dot is angular velocity, and theta double dot is the angular acceleration. Okay, is the angular acceleration, angular velocity, angular acceleration. Okay, fine. This is what? So this is the g tangential torque. So this should be what? Should be g tangential. Since it's a torque, you just multiply it with the length. Okay, it's this one. And it's this one, the friction force times L. Okay, now what is g tangential? Well, g tangential, if you look at the angles here, okay, it's g sine theta. This is gt. It's g sine theta. So you get this equation, ml squared theta double dot is minus, then you put everything without the dots on the other side, and you get the second order differential equation governing the rotation motion of the pendulum. So you get ml squared double dot is minus gt, so minus g sine theta L minus F friction force L plus Tc. Now the friction force itself is given or is proportional to what? Usually the friction force is proportional to the velocity. In this case, the viscous friction with the air is proportional to the angular velocity of the pendulum. And we consider it to be linear. So this is a linear dependency. So you can easily get, that's why then you just divide everything by ml squared. So you divide by the inertia, and you get here minus g over L, okay, because g is mg. So you get here g minus g over L sine theta minus k over m theta dot plus Tc over ml squared. Okay, it's very easy. And this is actually the differential equation as we need it to subject to our analysis. Okay, so didn't work. Okay, right. So essentially, yeah. Essentially, okay. All right. This is we just write from this equation to show us the way the pendulum is behaving. Of course, the question is how to solve such an equation. How to solve this is a second order equation. So the separation of variables is no longer applicable. It's not so easy to do any longer. So let's see what we can do about it. Okay, so the friction force is written here. So we have a nonlinear differential equation leading to a nonlinear model. Okay. It says here to get a state space model of the form 2. Let's see what the form 2 is about. So we need to write such an equation. So we need to get everything into first order. We have second order now. Can we transform this into first order? Of course we can. Of course we can. We choose as state variables the angle. So x1 is theta, and x2 is the rotational velocity theta dot. So essentially, x2 is x1 dot. But this is typical for mechanical systems. All mechanical systems have this first equation. Okay, because most of the mechanical systems are governed by second order equations. 1 second, please. Right. Okay. Fine. So if now we can write the equations depending on x1 and x2 because we made these notations, this notation and this notation. We analyze the free evolution of the system. We assume, of course, first of all, we assume that the external force is 0. And what we get eventually, what do we get eventually? So the first equation is position, angular displacement dot is angular velocity, and then angular velocity dot, which is the acceleration, is minus g over L sine x1 minus k over m sine x2. Okay? Now, the equilibrium points mean we need to set the dynamics to 0. So we solve this equation. X1 dot is equals x2 dot equals 0. And we get this algebraic system. Now, of course, from the second equation, since x2 is 0, the second equation becomes solving sine x1 is 0. And we know how to solve it. It's the third time we run into this equation. We come across this. And the equilibrium points are n, p, and 0. So if we have the pendulum, this is the pendulum, okay? So we have two equilibrium points. One is at 0, okay? So one equilibrium point is here. And where is the other equilibrium point? The other equilibrium point is here, okay? Okay? These are the equilibrium points. These equilibrium points correspond to the points 0, 2 pi, 4 pi, and usually 2k plus 1, 2k, double k pi. Okay, and these here correspond to pi, 3 pi, and of course plus minus, actually. Plus minus. This can be plus or minus. Plus minus, plus minus. Plus minus 5 pi. So in general, plus minus 2k plus 1 pi. 2k plus 1 pi. Now, the question we address is, what is the significance? Which one of these points is good? Which one of these equilibrium points is stable? Which one of these equilibrium points is stable? What do you think? What's your opinion on this?
The one below, due to
the one hanging. And how do we assess that? So if we make a slight perturbation, okay, say in this part, the pendulum will swing, and if there is friction, finally, it will stop. So it will always come back to this equilibrium point. So it's kind of a stable behavior. You agree? It's a stable behavior. What happens in this case if I make a slight perturbation of the pendulum to this side? What happens? What happens?
It won't return to
it will
its
fall
position.
exactly, and will never return back. So I'm going to make this sign, never come back. It will never come back. So stable, unstable. So this is a qualitative, intuitive assessment. Okay. Hold on a second, please. Let me stop these people writing to me. Right. Right. So where were we? Okay. So stable, unstable. So let's discuss a little bit about it. So from a physical point of view, the point, well, physically, there are only two equilibrium points. Mathematically, there is an infinity of equilibrium points, okay? So 0, 0, and pi 0, corresponding to the one to the horizontal, to the up, down, up, not up, sorry, not up, down, downward position, and the other one to the upward position or of the mass, both of them vertical. Okay, so the bottom one, the downward one, the hanging one, is a stable point, whereas the other one is unstable. We have the intuition about it. Of course, at a certain point, we need to formalize this properly. Okay, we cannot rely on intuition every time we see a nonlinear phenomenon. Okay, so what's the significance of the rest of the points? They're all the same. They're all the same. Okay, so they are just, so there is an infinity of trivial trajectories or trivial solutions, but they all have the same value. You see what I mean? So qualitatively, they are an infinity. Quantitatively, they have the same behavior. They have the same behavior. What happens when there is no friction? That's a good question. What happens when there is no friction? So even if the pendulum is hanging, okay, I'll just make it longer. What happens when there is no friction? K equals to 0. What happens? What happens?
It will spin faster.
Not necessarily. But if you just give it a nudge from the vertical position, what will happen?
I think it's not spinning, but just energy.
Not spinning, not spinning. It's a different word. Swinging, maybe you want to say swinging, right? It will swing forever. It will never stop. So it's something like this, the behavior, right? It will never stop. It will just keep swinging, and never stop because there is no friction. It will never stabilize to a constant value, but it will constantly swing, Of course, this is stability in the limit. Okay. So this is what happens to the pendulum. Okay. This is a very good example. Of course, you can linearize the pendulum. We'll talk about linearization quite a lot in the starting with the next chapter and then continuing when we study second order systems. Okay. All right. Now, another interesting model is the model of the neuron. Okay, where this is a biological picture. This is the sketch of a neuron where you have dendrites, if you can see here, which get the dendrites collect inputs from other neurons. Then there is the axon, okay, sending the signal down the axon. So the axon is acting like a transmission line. Okay, then you have the cell body, and then you have the terminal branches. These are the outputs. The terminal branches sending the electrical, because they are probably electrical signals, sending the electrical signals to other neurons to capture and to do the same thing. So the neuron is actually one cell, the soma. You have axons and dendrites. So the information transmission is this is for the information transmission, and you have the synapses, which are neural connections. And the question is, how do neurons communicate with each other? What's actually going on, and how can we describe this process and write a physical and/or mathematical model? Neurons communicate using exchange of ions, natrium and potassium. Okay, natrium and potassium. Changes on the ion concentration inside or outside the neuron are generating voltage spikes. These are all electrical impulses, okay, transmitted to the synapses. Okay, and the dendrites of the other neurons are just receiving and catching these signals. Okay, they're catching. So this is the way that actually works inside the neurons through the concentrations. So probably this is going to be like some sort of an electrical circuit. The neural activity, which is the state of the neuron, depends on the membrane potential. The membrane potential is influenced by the so-called postsynaptic potentials, which can be excitatory or inhibitory. This is important. So these are the types of signal we are interested in. Okay. So you have an activation mechanism and a signaling. I wouldn't say signalization, signaling mechanisms, which can be identified. Okay. So this is the biology of things. It's not very easy, and then you have to transform this biological information into physical and mathematical information to be able to write a model. Okay. To be able to write a model. So what they came up with is they say that the neuron may act as an resistor capacitor circuit or an RC circuit, okay, which has this graph, this picture, okay, described by this by picture in figure 4. Okay, look at the concentrations. Do you see? So this is the equation governing such an electrical circuit, okay, such an electrical circuit, where AJ, GJ, and IJ are the equilibrium potential of the ion conductance and the current on the channel, respectively. It says here. In stands for the current injected into the cell, V is the membrane potential, and C is the electrical capacity of the membrane. So the equation governing so the model, you see, it's so this is if you can see here, this is a capacitor law. Okay, this is a capacitor law, right? You know that the current through a capacitor is C, the derivative of the voltage of the capacitor voltage. Okay, C is the capacitance. And you have this model. This is a nonlinear model, okay? This is a nonlinear model because most of these guys depend on time. This is a state. This is also a state. So this is not a linear model, although the equation looks very linear. So let's not be fooled by the shape of the equation, okay, itself. This is totally a nonlinear model, okay? One second, please. Right. Right. Let's see. Let's go further and have a closer look. The conductances, it says here, GK and G potassium and G natrium, do depend on the membrane potential. So they are functions of the potential. So this is nonlinear. So we can write easily. It's not easy, of course. It's a very difficult way to write this model. A two-state variable model. Okay, a two-state variable model, like this one here. Okay, so now you have two states, and the general model that can be drawn mathematically from this physical model, of course. So it's another simplification. Is you get these two equations where where gx is a sigmoid function. Why is it called a sigmoid? Because its graph looks like this, like an S. This is a sigmoid function. Okay, this is a sigmoid function. And you have the equation of the activation and the equation for signaling. Now, this is a very simple model if you look at it. It's a simple model and it can be analyzed. The question is, how can you deal with it? Or how do you deal with it when you have a bunch of equations? So, and you get a neural network like this. How do you do? Of course, the model becomes big and it surely needs approximation. Of course, we do not get into the details of model approximation right now. I did this last semester. I'm not going to do it very much now. So this is where we're left with it. So we have this model of a neuron. Now I would like to show you. Let's see how we do this. I would like to show you something very interesting. I did not have much time to put this into the slides, so I'm just going to present a paper. Well, this is a research master, so let's talk a little bit about research papers. Last year, when this bloody pandemic started, and we started to do online studies. I'm not sure whether you remember or not. I'm talking now to the people who are studying at this university. Last year, we started the second semester, if you remember. We started it physically, and not last year. Last year. I'm talking about the second semester that started last year in 2020. Okay, so in 2020, school was supposed to start somewhere in March, we went to the university physically, face to face for like 3 weeks, if I remember correctly. We had approximately 3 weeks to go to the university, and then the emergency state was put in place, was declared, and then we had to turn to the online system. You remember that? I guess so. I think Andrea and Theodor, you were 4th year back then, weren't you?
Yes.
Yeah, so that makes sense. 4th or 5th, I don't remember exactly. The thing is, I'm sure it had to stop. So we did all the lectures online the way we could. We didn't have Teams back then. So everything was uploaded on Moodle, and then you just read and you just did the quizzes and did whatever we were asking of you to do. And I was looking at things to see how do these things behave. And in the middle of the semester, I was looking up on Google, writing COVID spread modeling. Just typed COVID spread modeling, tapped this into the computer, and I found this result. I'm not sure whether this paper is now published or not. I have to look it up. But I found this preprint of this paper on something on a network called medRxiv, presented by these people in Morocco, writing a simple model of the COVID spread. Okay, so they wrote this paper and trying to show how the virus is spreading throughout specific countries. And if you look on the second column of this page, so the purpose of this paper was to consider a mathematical model to study predictions of the outbreak of the coronavirus in the most infected countries in the world. So, such as USA, Italy, I'm not sure whether you remember or not the Italian situation back then, Spain, Germany, Iran, and France. Of course, China is excluded from these considerations. And of course, how do you want to reduce the seriousness of the coronavirus? So they cooked up this 4 equations model. So for the time being, I'm just showing you that you can have more than 2 equations in a nonlinear model, and you get these equations. You get these equations. Okay, you have 4 variables, ST, 4 states. ST are the susceptible people at time t. IT are the infectious people or the infected people at time t. RT are the dead people, let's put it bluntly, removed, okay, more or less dead people at time t. And C are the exposed people at time t. Okay, not very much taking into consideration. So this removed essentially is dead, because I wouldn't say it's about the people who got cured. Okay, it's not. They don't talk about people who get cured here. So maybe it's not a very accurate model, but it's a model. Okay, and of course, if you add up all these 4 states, you get N, the total population of these countries, the total population under study. Okay, what is alpha? So we have some coefficients: alpha, sigma, and beta. These alpha is the average number of infected people by contact with one symptomatic individual who has been infected. So the contact with an infected is alpha. Okay, the average number of people getting infected by through the contact with another infected guy. Gamma is the infections rate, the incidence. Yes, is that number that you hear from or you hear on the telly every day. Okay, the case number, the one that was supposed to, for instance, to close the schools or the restaurants. Okay, now nothing happens, but that's a different story. Sigma is the death rate, I'm afraid, is the death rate. That's why I'm saying that removed is actually dead people, if you ask me. Okay, so we assume that the population, of course, I just said that the population number is constant. Okay, so we are interested in the predictions of the outbreak of the coronavirus. Okay, for 15 weeks. It was this, for 15 weeks. Okay, and they have a lot of numbers. have a lot of numbers here, and they show all sorts of graphs for different countries, What I did myself was a bit different, in the sense that I tried to find some equilibrium point. Okay, and here they make an analysis of equilibrium points. Okay, they do compute equilibrium points. They do try to make an analysis and see which one of them is stable and which one is unstable, because you can do that. Okay, this is not very much. I have to look it up if they have an improved version of this guy. But what I did, and I'm probably try to show you a little bit later, is that I ran myself some MATLAB simulations. I tried to numerically integrate this guy and see and check the results. Okay, and the results were actually not very pretty, I would say. They are interesting, but not very pretty in the sense of our health and our state of living. Right. So now we have to talk about classes of nonlinearities. So how do you decide on the nonlinearity of a system's element? This is the main question. By deducing a mathematical model, so you look at it, sine x, cos x, x1, x2, these are nonlinear elements, okay? They are nonlinear behaviors within the system, meaning that you cannot apply on such equations the Laplace transform. This is the main decision. This is the main ingredient telling you whether some equation is nonlinear or not. If you cannot apply, if a state or a combination of states or a function of states is not possible to be subjected to the superposition principle, essentially, there is no Laplace transform, so that's a nonlinear equation. Okay, so from experiments, observing that the superposition principle is not satisfied. Okay, exactly what I said earlier. Okay, so there is a distinction. We have weak nonlinearities and essential nonlinearities. The nonlinearities we mainly discuss in this class are weak nonlinearities, such as sine x, polynomial, square root of x, and so on and so forth. This is weak nonlinearities. But you also have essential nonlinearities, which are a bit more difficult, and they are a separate case, and I'll explain in a minute why these need to be treated separately. For instance, it says here, gx is sine x. This is a weak nonlinearity, okay, because we know how to deal with, and because if you do linearization, you can easily approximate sine x with x for very, very small variations. Whereas with the essential nonlinearities, you cannot do that. Okay. So near x0, of course, gx can be replaced by hx equal x. This is something we know from physics, from our high school studies. Okay. Of course, this is due to the linearization principle we are going to study pretty soon. Okay, you linearize things through Taylor series expansion, and you extract the first order terms, and then for very, very small variations, you can claim that indeed sine x is almost x. Such functions, they say here, they are smooth enough, or at least continuously differentiable. That's why they are weak nonlinearities, because they are like this. However, essential nonlinearities, they are all discontinuous. They are of relay type, and they are frequently encountered in control and automation. Okay, these are saturations. These are sectors. Okay, discontinuous nonlinearities raise a fundamental problem for correct modeling. Okay, redefining the concept of solution. This is very, very important. So the concept of solution of the Cauchy problem we discovered earlier. This is peculiar to smooth or mostly mildly discontinuous or piecewise discontinuous with discontinuities of finite limits. Okay, finite limit. These are weak nonlinearities, and we define the solutions for such nonlinearities. So for these essential nonlinearities, you have to bring up and you have to come up with a new concept of solution. Okay, a new concept of solution. Right. One can define, they say here, different types of solutions. One might be interested in one type, while numerical integration methods may converge to another type. This is another issue that happens to essential nonlinearities. Okay, so we have saturations. Saturations looking like this. Saturation of sigma is sigma if, this is if here, sorry, if. Okay. Let's put it in English. If absolute value of sigma is less than 1, and sine sigma if it's larger than 1, then you have, and sine of sigma is minus, so it's a signature definition. This is -1 if sigma is negative, 0 if sigma is nil, and 1 if sigma is positive. This is the sign. We have sector time nonlinearities, and I would really like you to keep in mind this type of nonlinearities, because we are going to study this in chapter 5. We can get specific stability concepts for such types of nonlinearities, and actually we are going to get frequency domain. It's very funny. Frequency domain criteria discovered by Popov, the Romanian Popov, to assess specific stability for a specific class of nonlinear systems, i.e. The class of nonlinear systems where the nonlinearities are static. Okay, the nonlinearities are static, not dynamic. Okay, so this is what a sector looks like. Essentially, it says that the function phi of sigma, okay, takes values only in this sector, only in this sector. Okay, all right. Okay. Sector time nonlinearities. Nonlinearities, then we have nonlinearities satisfying a Lipschitz condition. Okay, you know Lipschitz conditions with a Lipschitz constant. Okay, you must have heard about this. And you can have also monotone nonlinearities such as this one. Okay, such as this one. Okay, so these are essential nonlinearities which are crucial. They are very important. Okay, for the development, for understanding the development of nonlinear systems. We are going to mainly rely and mainly discuss the main concepts of this lecture of nonlinear systems for the weak nonlinearities. Okay, for the weak nonlinearities. So finally, what is linear versus nonlinear? We can also have feedback connections which are linear and nonlinear as well. Okay, so one way to look at things, and this is something we are going to do at certain point. So you have here a linear system, okay, U, Y, and then you take this, and then you put here a static nonlinearity, and then you plug in this guy, and this is your nonlinear system. This is your nonlinear system. Okay, we can do that. So this is a nonlinear. This is a nonlinear state feedback. This is a nonlinear state feedback. Okay. All right. Feedback control design says here must cope with special operating conditions and limitations due to sensor actuation characteristics. So this in when you have actuators and sensors, they might reach saturation, and then you get nonlinearity. You get even essential nonlinearity. Okay. when you go to linear, from linear to nonlinear, from the variety and the vast world of linear systems, what do you actually lose? This is a good question. What is lost? Okay. First of all, the superposition principle, and actually, all of these are the second one is a consequence of the first one. Of course, automatically you lose the Laplace transform, you lose the Fourier transform, and eventually you lose the frequency design methods. So there is no frequency domain for nonlinear systems. They tried to invent through Volterra series expansion. They are trying. They tried, and now apparently they try again to invent a frequency domain for nonlinear systems, but that's very cumbersome, and it's not actual frequency domain in the sense of how we know it, of Laplace transform, okay, or Fourier transform. Of course, in the case of nonlinear systems, the uniqueness in the existence of the solutions is not guaranteed any longer. It's not guaranteed any longer. Okay. So for now, how do we deal with nonlinear systems? So we study them in the state space framework, not in input-output behavior. So we look at the state space behavior. So we are going to use differential equations mostly, and of course you would need to use not only geometry, but actually differential geometry, which is something really difficult. I'm not sure if you people ever studied differential geometry. It's something terrible, if you ask me. I never understood it, and I probably never will be able to understand it. We are going to deal with some differential geometry in the very last lesson of this class, somewhere in January or at the end of December, or even earlier, because I intend to stop presenting theory a little bit earlier to give you time to study papers and to talk to me, to discuss research. Of course, in some special situations, however, in some special situations, and actually is the situation I showed earlier, the situation I drew here, in some special situations, you can get some frequency domain criteria for stability, and we're going to study that, and it's going to be a little bit funny, okay, to be able to assess the stability of a nonlinear system using a frequency domain criterion. All right, okay. Right. Okay. Sure. I would say let's have a short break, and I'll try to show you something in MATLAB next. Okay? Let's have a short break. Do you agree? Because I think there is a lot of information to process, and it's not very easy to sink in. Okay? Let's have a short break. Let me try to show you something in MATLAB, if I can, and then we'll see what we can do. Okay? And then, of course, I need to show the model because I need to show you your assignments for this class. Assignments are already prepared, and I would like you to solve them because I give you points for those assignments. Okay? Right? Fine. So let's have a break, and I'll see you a little bit later. Okay? Fine? Please don't go.
Yes, it's fine.
Fine.
Teacher, we can see your tablet.
Yeah, I stopped share screen thing. Sorry about that. I forgot to kill the share screen, but that's fine. You didn't see much anyway. No worries. I'm trying to put something on Revolut because I need to pay something and I'm unable to do that. And I honestly don't understand why.
For me, it's not working, Revolut. It's not working to add money to my account.
Why not?
I don't know. They say it's something wrong with their system. I've already contacted their help center. But this is happening for like, I don't know, maybe 2 days.
I see. Right. It's weird. I thought Revolut was supposed to help us.
I think they have some issues with their banks because the money on Revolut is somehow guaranteed by banks. So I assume money is in a bank account.
Yeah, it's yeah. I'm afraid that Revolut will disappear someday. I don't know why.
And in my case, the error says that to contact my bank because there is something wrong with my bank. But no, they have issues.
I understand. Oh, so now it worked actually. I did something wrong as well. So yeah. Mama, mom, mama. I've been trying for the past 10 minutes to start my MATLAB. I don't know what's going on. Damn. I'll try again. This is not normal. I actually don't know what's going on, but I'll try to fix it. Why isn't it starting? It shows the logo. It's trying to do something, but nothing happens. Well, in the meantime, I will try to show you the Moodle and the material uploaded on Moodle. Can you see this computer screen?
Yes, it is visible.
So this is the Moodle of your class. You have all the chapters we are going to present on the OneNote class book, okay? And then you have here books. I'm going to show you books. Here you have, and I'm telling this to our friend Florian, because here there are some books and some lectures from some good universities on this, okay? Especially about feedback linearization. And then I have the book of Khalil, and I also have the book of Khalil with solutions manual, because the book of Khalil contains in each chapter quite a number of exercises and problems. And here you also have some solutions. And I also have a book about L2 gain and passivity of Arjen van der Schaft, published in 2000, a famous book and a very good handbook. Right. Let's go back to the main. Okay, so what else do you have? Here you have the papers to study. And here is where you're going to pick 1, 2, or 3 papers or whatever for your final exam. Because I suppose you're only 4 people. So you can each pick at least, I would like you to each pick at least 1 paper, okay? 1 paper. Some of them are published by myself. The others are published by some other people and contain other topics of nonlinear control systems, okay? So you pick a paper and then this is going to be your final exam. Study the paper, fill out a report about what you understand, what you do not understand, and how you can improve the paper or not, and implement, if possible, the examples of the paper. So this is how the paper and exam folder looks like. And then you have some problems. Oh, this is in Romanian, I'm afraid. This is not helpful for Florian. Problems of nonlinear systems solved. Okay, maybe you can show it to Florian if he has questions about it. These are problems from different books solved and presented with the solutions handwritten by myself. And this is my YouTube channel where you can see last year's lectures of this class, if maybe I said some other nice details about it. And then here we have from last year, written on the graphic tablet, a material by my colleague, Professor Radu Ștefan, who last year helped me, a material about numerical integration, okay? About numerical integration, okay? So this is how you look here you can recognize how do you solve such a system? This is a question we need to answer, okay? So we define the concept of solution. Now we wonder ourselves, how can you find this solution? Of course, analytically is very difficult. I showed you, okay, for simple scalar system, this is easy. You merely apply the separation of variables principle, and then you simply integrate. However, this is not possible when the order is larger than 1. So from second order system onwards, it's next to impossible to find or to determine an analytic solution using only the pen and the paper. Hence, we do need the computer. And if we do need the computer to numerically find the solution of the Cauchy problem, then we have to use numerical integration. We have to use numerical integration in the sense that in numerical integration, numerically, what does MATLAB do? It computes some sort of approximation, discrete approximation of the solution at various moments of time, depending on the initial condition, and that is approximately the analytic real solution. And there are powerful mathematical theorems and results proving the closeness of the integration methods. We have the Runge-Kutta based integration methods, ODE 2.3 and ODE 2.5 in MATLAB. So what happens? The first order method is the method of Euler, okay, where you approximate x dot. So you approximate the time differentiation like this: xn minus xn minus 1 divided by h. H is the step, okay? H is the discretization step, if you like, okay? And this is ftx, which is actually f. It's a recurrence. It's f. It's a recursive relation. F of t at moment n minus 1, and the solution, the point of the solution at xn minus 1. And then this leads to this equation. Xn is xn minus 1 from this plus h times the previous point, the solution at the previous step, okay? And the moment in time Tn is T0 plus the step times T at moment n minus 1. H is the integration step. This can be constant or variable. And we have methods ODE 2.3 and ODE 4.5 in MATLAB. These we can also have higher order methods, okay? Difference equations of order 2, 3, or 4, 5. This is what it means. Okay, the order of n, 2, 3, or 4, 5 steps. Okay, this is what ODE 2.3 or ODE 4.5 means. In the meantime, let me check. No, the MATLAB is not starting. There's something wrong. I should restart the computer, but this is going to take a while. So if you can bear with me for a little bit. Right. What it says here? Interaction between message. Okay, and here there is an example of a model and the way to try to integrate it. So I told you that the MATLAB is starting, so this is good. So probably I think there was the antivirus doing something, or the anti-malware program doing something to it. That's why it took so long. Coming back, I told you that my colleague Professor Radu Ștefan is working on biological system stuff. For instance, he shows here an example of the interaction between the messenger RNA. If this isn't today's subject, what is? And the microRNA. These are concentrations M and mu. And you have this simplified model of two equations, okay? And this can be integrated. So you can take this as an exercise. Take this model, this biological model, give it certain parameters, and try to simulate it. Try to simulate it. So a little bit about numerical integration. You can study this. This is on your Moodle. This is on your Moodle. Okay, and I want to show you that starting next week, you'll have assignments. Starting next week, we'll have assignments. Okay, doing numerical integration. I'm going to give you, I'm going to put on the files class all my M files of numerical integration, so you can have an inspiration and a model to try to work them out yourselves. So next week you'll have this assignment, which would be nice to, oh no, here you have the, oh, by the way, you already have, I forgot, I already uploaded M files and also Maple files. Try to find Maple as well if possible. I'll show you next week. So you do have here some examples, so you can work out this assignment. Okay, I'm going to open this assignment for next week, and I'm going to leave it open for a couple of weeks for you to submit a solution and be graded. Is this all right with you? If you have any questions about this. So you will have a few assignments along this this class, okay, along the semester. I would like you to solve them to be able to get points. Okay, I'm going to grade you for your answers. You can answer written and scan. You can answer using MATLAB files, text files, Word files, whatever. Just upload stuff and show me how you solve these problems. If you have any questions about this, please.
It's totally fine from my side.
Okay, so please solve them. You see that every 2 or 3 weeks you get an assignment. You see? You get an assignment. It's only 4 assignments. It's not very much, I would say. So you have enough time to sort them out and to understand what's going on. I hope this is acceptable for you. I don't want to put pressure on you, but at the same time, I can't just let you do nothing. You agree?
Mm-hmm. Yes.
Okay, fine.
Fine.
So this is pretty much it. Now MATLAB is on, so lucky us. Let's open some files. I have specific files for this class. I used them last year as well, and I'm going to use them this last instance of this course. As you know, this master program is not going to start again this year because there were virtually no students registered for this course. So let's see. Let's do somewhat. I have here some models. Let's see Lab 1 ODE. What is about. I'm opening it. So you see a differential equation, a scalar differential equation, and the software to perform numerical integration. This is something we need to understand. If you understand numerical integration, then simulation for you at this class is going to be a piece of cake. If you clearly understand and take a little time to study numerical integration. Of course, you can also go to the internet and look up all sorts of materials if you want to dig or dive into the details of such approaches. So how do you define the solution? Okay, how do you define the equation and the solution? First of all, you define the equation. You build up this variable dx dt, I call it, to be, so it's a suggestion. Then you have to refer to these arguments, so it's in arguments t and x. And this is the Riccati, for instance, scalar differential equation. It's the Riccati ordinary second order ordinary differential equation. And here you get the initial condition. Okay, x naught is minus 0.5, and then you span your time framework. So here you have the time axis. So you take the moments from -5 to 10 in 50 points. This is your time. Keep in mind, this is numerical integration. So you have to give the number of points. Yeah, the number of points, time domain to compute the solution. And then this is the numerical integration step. This yields the solution found through numerical integration. And here you can use, let's see, first of all, let's try ODE23, like I said. So in only three, a recursive relation in only 3 steps, yes? And then you just plot. We plot the solution, and we also plot the vector field. We also plot the vector field with respect to S. This with respect to the solution, okay? So this is an important plot. You'll see in the next chapter we are going to present next week that the plot f of x versus x for scalar systems yields stability criteria. Yields stability criteria. If you'll excuse me 1 second. Sorry about that. Where were we? Okay. So here we plot fx versus x. We'll see next week. This is an important. This is the vector field, the dynamics plotted versus the solution space. Okay, x. And this is very important. You'll see it next week because it determines equilibrium points, right, where f is 0, and it also determines the stability of the equilibrium points. So let's run this guy. Let's run this guy. Add to path. Add to path. You see? One graph. Okay, so this is the solution versus the time. As you can see, probably if we look closely, we can see that in this point, there is an escape time. So there is an asymptote. That's why it probably looks like that. And here we can see, here on the second graph, we can see so yeah, the plot of f of x, which is a second order scalar function with respect to x, of course, yeah, and a single equilibrium point in 0, which is this one. I'm sure this is okay. So here where my mouse is, where I'm pointing with my mouse, that's where the equilibrium point is. Let's look closer at the plot. You see, this is where the equilibrium point is, because this is fx. Maybe I should add legend. No, x label. So this is where do I add the x label? It didn't do nothing. And this is weird. Okay. So insert x label. No, there is nothing. Let me just use the code. X label equal solutions x, and y label fx. Maybe this is much clearer to you. Makes things clear. F5. Yeah, fx. And oh, why don't we see the x label? Anyway, there's something wrong, but anyway. So this is fx versus x. Okay.
I think you need to remove the equals sign. Then it works because it's just a function call.
Oh, sorry. This was a mistake. Why did I do equal? Sorry about that. No, what's wrong now? Oh dear. Solutions X. What's wrong now? X label is not correct. Like this should be equal, or not here.
Maybe you need to use the close all command to close all windows one time, because it might be now that you have like more than 2 plots or figures open. Maybe that's the problem, because they get
But
open.
it gave an error. It says error here, you see. So I think this is usually how you do X label and Y label, right? And title, like this, right? Huh? This is how you usually do these commands. You agree?
I think so, but it has been some time since I used MATLAB the last time. But you can use like doc or help and then the command, and you will see how it needs to be done. In the
Yeah, help. I can do help. Yeah, I know that. Help. Maybe I don't know something, or maybe it's not called X label. Oh. Hold on a second. What am I doing wrong here? Title. Okay, that's clear. X label. Is a variable of time character. What's that supposed to mean?
maybe try doc instead of help, then you will get like the full documentation.
Oh, okay. Doc instead, but it should be enough. I mean, this should be enough, because Y label works. X label is not working. This is the funny thing, because Y label works. X label is not working. Well, never mind then. You understand what I want to say. Because I'll do this later. You see, Y label works. Funny. So this is fx versus x, makes sense, okay? And this is x versus t. This is x versus t. So let's see. Let's see if you do this positively. Let's go from 0.1 to 10 in 50 points. Okay. Yeah, so you see, once again, you see there is an issue. So there is a finite escape time. Look where it stops. This is a finite escape time model, and it makes sense because it's the solution of the Riccati equation with this type of condition. Let's do a different condition. Let's take one, see what happens. You see, it's a different solution. No finite escape time any longer. Not finite escape time any longer. So the initial condition is very important. Look, now it's a different initial condition, and you can see that the solution is stabilizing at 1. Okay, so probably there is bands of solution depending on the initial condition. So the initial condition sets determine bands of solution. Let's go to -5 and see what happens. Let's run it. Oh, nothing happens. It's too much. Let's go to -1. Yeah, you can see again, this goes to -infinity here in 0.7. Okay. And let's go to 0.5. Yeah, you see 0.5. It goes, so this is a band. It goes from 0 to 1. You see, it goes from 0 to 1. So there's different bands of the solution in time depending on how you initialize this this equation. So the initial conditions are crucial. Keep that in mind. Now I'm using ODE 4.5. It looks, the graphs are in some sense a bit clearer now. They're a bit clearer now. Let's see if the initial condition is 0. Probably nothing happens. Probably nothing happens. As you can see, constant. Nothing happens. What else? Let's go to very low initial condition, like I said, -10. Let's go again. Oh, nothing happens here. So this is no band here. Let's go to -0.1. We'll study this analytically next week. Okay, starting next week, we'll study this analytically. How do we compute these solutions depending on the initial conditions? But this is how to perform numerical integration. Okay, this is how to perform numerical integration. Okay, so this is one case. Now I'm going to show you numerical integration of more complicated stuff, such as the Lotka-Volterra predator system. Lotka-Volterra predator system. In the first file, lotka.ode.m, we define the Lotka-Volterra predator-prey model. We just write it because this is a system of two equations this time. So we define the function dp dt. We give it a name, Lotka-OD, depending on time and on the variable p. P is the state variable. We have some coefficients here. And here we have the two differential equations. P1 dot is P1 times 1 minus beta P2, and P2 dot is P2 times minus 1 plus delta P1. Okay? So this is how you write the differential equations. Okay? And this is how you define your differential equation. Now, we go to the integration part. This is the integration part. Okay? This is the integration part. Initial time 0. Final time 70. So we simulate this between 0 and 70. The initial conditions are 10 and 20. So we have 10 predators and 20 prey, so to speak, prey. Yeah? And here we just numerically integrate. We numerically integrate using ODE45. Okay, and this is the syntax for numerical integration. And then we just plot the solution P of t. We just plot it. Okay. Okay, and then okay. Oh, and then we do, because this is a second order system, we cannot plot f of x versus x. But here we can plot x2 versus x1. This is called a phase portrait. Maybe you heard of this term before. Yeah. So for second order systems, we are going to use quite a lot phase portraits. Let's play a little bit. Run. Something happened. No, this is something wrong with MATLAB, I'm sure. I don't know what's wrong with it, but it's not working properly for some reason. Look at the solutions. This is P. This is P with respect to T. So look at the solution, P1 and P2. You see? P1 and P2. P1 and P2. I'm not sure exactly what's wrong with this MATLAB. What I'll try to stop it and start it again. Okay? So please bear with me for a second. Where is it? Because there's something wrong. I'm not sure what's wrong with this instance of Windows and MATLAB, because I had no problems before. Everything was running smoothly. This time there's something wrong with it. Okay? So let's try again. You have all these files uploaded on Moodle, okay? Please play with these files to be able to understand numerical integration a little bit. Okay, because there isn't very much else I can tell you about it. Okay, this is, keep in mind, MATLAB is working with numbers. Maple is a symbolic toolbox. Okay, Maple is a symbolic toolbox, so deals with these things a bit differently, has different, some kind of different algorithms to sort out numerical integration. Where I have to look here, software. Let's go to this. Okay. Yep. Yeah. It's working very nicely. So now you can probably see, look, the evolution of the prey and the predator, the evolution of the prey and the predator in this system You see, this is population. So red is predator. So the predator is increasing. Look, increasing. Look at the evolution. It's very interesting. Okay, and this is the phase portrait. So this is predator versus prey. Okay, this is the phase portrait. This is a geometric concept. Okay, predator versus prey, and it's very interesting. You see, it's a limit cycle. Do you see that? It's a limit cycle. This is specifically nonlinear, so it's oscillating all the time. This is a limit cycle. Okay, so now you can play with the initial conditions. So if you have 1 predator and 20 prey, look, you see, it's a bigger limit cycle. So the evolution is slower, is very, very slow. It's very, very slow. Now, if you have 10 predators and 2 prey, you see, it's another limit cycle. Again, it's rather slow, but it's a big oscillation. Okay, it's a big oscillation because there is not much prey. Let's see what happens if they are equal to each other. Maybe I should just close these and start again. You see, prey and predator. It's always that the prey is lower than the predator. You can see that from this model. Okay. Let's see what happens if one of them is 0. Okay. Let's see what happens if one of them is 0. Look, if there is no prey, it's unstable. The evolution is unstable. You see, the evolution is unstable because it's only prey, it's only predator and no prey. So nothing. It's not a good it's not a good trajectory. It's not what you like. What happens if there is only prey and no predator? Look, the prey will finally die out. You see, it'll go to 0. You see, and this is constant. So the predator is 0 on the vertical axis. Okay, let's run this again. Yeah, look, and this is the phase portrait. Predators evolving. Yeah, predators going actually they eat each other essentially. This is what it says. If there isn't, sorry, the prey. But the predator says here. No, this is different. I think it's the other way around. Yeah, between the variables. Okay, but it's interesting. I think it's very interesting here. One of them dies out. So you can play with these files. You can play with these files and see what's going on. And this is how to deal with it and how to understand it. Okay. Now let's open, what else? Let's open the pendulum. Open the pendulum. Pendulum ODE. So this is how you define the differential system, the first order differential system of the ODE. You can also deal with, I think, with higher order equations, but I don't know exactly how you're able to implement them in a MATLAB file, but I suppose you can do that, you know. I suppose you can do that. Okay, so this is the pendulum ODE. So you have the mass 20, the length of the rod 10, the gravity constant 9.8, and the friction coefficient K equal to. And these are the equations. You can recognize the equations, okay? I'm not sure why here we don't have the sign, because there isn't a sign here. If you look closely, it should be like this, right? There is no sign, no sinus involved, so it should be a sinus here. And then we open the simulation file, which is this one. Okay, look at the simulation file, same thing. Initial conditions, so angular position 0.5, angular velocity 0.2. So you start, you let the pendulum swing from this position, 0.5 displacement, 0.2 velocity. Okay, and you just let's run the simulation, see what happens. Well, Well, look at the simulation. So if we have friction coefficient K equal to 2, so the position and the velocity are both of harmonic behavior, okay, with a phase difference. So they have a phase difference, okay, and it's slowly dying out. It's slowly dying out. Probably if we extend the final time and run the simulation again, look, you see, eventually, but after a long time, eventually the oscillations will die out. Okay. Do you need these plots to be larger to understand, or can you see clearly? You can see clearly, right? Now, look at the second. Look at the phase plot. What happens to the trajectory in the R2? Yeah, R2 in the geometric space. The trajectory will probably converge to this point. This is the equilibrium point 0. You see here, this is 0, 0. I should also get some grid on to the second plot. Phase plot grid. Why isn't it doing it? Well, it doesn't show a grid, but anyway, because it says here grid. Never mind. So you see, so this is the time plot and this is the phase plot. It's all depending on this. Okay, the initial condition doesn't change many things around here. Okay, let's put this to 100 so we can easily see something. Yeah, you see, it's dying out. It's dying out. Right, and now let's change in the pendulum. Let's see about the friction, because the friction is in. Let's first increase the mass 5-6 times. See what happens. See what happens. You see what happens? The swinging, and also this is in the first portrait. This is called a focus point. Focus point. It's a spiral. Okay, and we'll see what determines this spiral behavior. We'll see what's determining the spiral behavior. But look, you see now the oscillations, probably because it's the mass is so big, will die out very late, very late. Okay, let's go back here and change back the mass to 20. The length of the rod also. Let's increase the length of the rod and see what happens. Oh no, sorry. This is save. This run. Oh, if you increase the length of the rod, look at the different oscillations between the velocity and the position. Okay, between the velocity and the position. It's very interesting, huh? It's very interesting. And the focus looks differently. So the length is also very important. You see, the behavior depends heavily on the length of the rod. Let's put it back to 10. We cannot change the gravity constant. That makes sense. But let's change the friction coefficient. Let's make the friction very small. See what happens. Oh, not this one. Shit. It's always this one. Look, the oscillations do not die out. And look at the behavior. It looks like a circle. So this is a limit cycle. No, this is not. This is a center behavior. You would be tempted to say this is a limit cycle. No, this is not a limit cycle because this is not structurally stable. Why? Because if I change now this to 0.5, I change this to 0.5 and I run, you see, it's dying out. It slowly becomes a focus point. It slowly becomes a focus point. So let's make it 0.5. Save. Run. You see, it's already becoming a focus point. A focus point. So the behavior is changing. The behavior is changing. Okay. Okay. Let's see what happens if the friction is 0. Okay. Friction is 0. Just like we asked ourselves. You see, it's a circle. So this is, you'd say it's perfect oscillation, but this can never be zero because you have uncertainties. This will never be zero. This will never be zero. Let's take it, what it was, 2 or 3 or something, right? Okay, let's go back. Simulate, you see? So this is the behavior of the pendulum. The oscillations, because you have friction, will die out, both in velocity and speed. Okay, and depending on the mass and on the length of the rod, the oscillations have different shapes. The oscillations have different shapes. Okay. The way the pendulum looks like, okay, it will always have such a behavior. It will always have such a behavior. Okay, right? Okay. So the pendulum is a benchmark example. If we understand the pendulum, we pretty much understand most of the rest of the stuff. Okay, most of the rest of the stuff. Okay. What else? Oh, and I also have a van der Pol oscillator. Van der Pol oscillator is the model exhibiting the behavior of a limit cycle, which is a nonlinear specific model phenomenon. Okay. Now we see what permanent oscillations and structurally stable oscillations look like. And the van der Pol oscillator is doing that for us. Let's show the differential equation. Differential equations are easy. Van der Pol oscillator. We have this epsilon coefficient, which is usually less than 1. And these are the equations. These are the equations. Okay, you see, if you can closely look, this is a merely polynomial equation. There is no sign involved. Keep in mind that. Keep in mind that. Okay. So let's just run it. What now? I think I did something wrong here. Should be. Excuse me. Let me just fix this for you. Van der Pol. Okay. Sorry about that. Run. No, what now? Oh, sorry about that. We have to also pick up initial conditions properly. Yeah, initial conditions properly. Okay. So this is the position, the displacement, and this is the velocity. We can still consider them like that, even if there is no discussion. It's not a pendulum. But look, you see Van der Pol, you have constant oscillations, right? So you can take here 2000 and run. You see, constant oscillations forever. So this is a limit cycle behavior. Sorry about this 2000. Let's take it to 100 so we can see something nice. Yeah, you see, constant oscillations, constant, structurally stable, no matter about the perturbation. No matter the perturbation. Let's see what happens if this epsilon is increased. What happens if epsilon is increased? Run. It's the same thing. It's the same thing. What happens if epsilon is now, the behavior will change if epsilon is over 1. Let's take it 1. Save, Van der Pol, 1. You see, it still oscillates. Let's take it much larger, and then let's try to take it negative. Let's take it 10. Run. You see, the behavior has changed. It's a bit weird. It's still a limit cycle, but it's weird. Behavior has changed quite a lot. Behavior has changed quite a lot, I would say. Let's run this again. Yeah, you see, it looks very weird. What happens if we have here negative? Because you can also take epsilon negative. Why not? If this is simulation, you can do anything. Right? Run. Oh, you see, if you take it negative, then you have you no longer have beautiful constant oscillations, but it will stabilize at 0. Yeah, because 0 is an equilibrium point. It'll stabilize at 0. Let's see what happens if you take larger negative values. Let's see if it stabilizes. Nope, it becomes actually unstable. And this is called an unstable node behavior. It's a node because it starts from the equilibrium point 0 here and goes towards the unstable behavior. Look here, you see instability. Instability, okay? Something like finite escape time that probably indicates instability. So this is a node behavior, and we'll see how this geometry is induced by some eigenvalues of some linearized system, okay? The van der Pol oscillator. Let's take -1 and see what happens, and let's decrease the value of epsilon. There is no point in changing the initial conditions. You see, so if you take, this is again a node, but this is a stable node behavior, because if you can see, the trajectory in the phase portrait goes to 0. This plot indicates what happens here, because it goes to 0. So this is a stable node. So we saw an unstable node, and now we see a stable node behavior, okay? Is clear what I'm showing here, or is confusing? Please tell me. How do you feel about it? Hmm? Can you hear me, please?
Yeah, I think I will play around on my own again.
Yeah, play with it. But the graphs are interesting. I mean, try to understand the physical phenomenon from the simulations. It's very interesting. Van der Pol oscillator, that's why it's been created, because it's an easy system exhibiting constant oscillations, okay? Okay, even if perturbed. I mean, perturbations are small in general, are not like this. So you take a value 0.5 and then you take a value 100. That's not perturbation, that's crazy. Okay, that's just crazy. But this is very interesting about this guy. The constant oscillations. That's why it's so popular. And we are going to talk about the Van der Pol oscillator itself. We're going to show models and so on and so forth. How it works on using pen and paper, so to speak. Okay, using the pen and paper. Right. Okay, Van der Pol oscillator. And now I want to show you the COVID guy. Let's see, because the simulations of the COVID guy, they're I would say they're rather gruesome, so to speak. You'll see why, because everybody dies in the simulations. I'm afraid. There is no escape. Of course, unless everyone gets vaccinated. That makes sense. Okay. So COVID spread and COVID OD. Let's try to open them both simultaneously. Right. So here I implemented the model I presented earlier in the article. Okay, this is the model presented earlier in the article. So all the coefficients. Population is 1,000. Per capita death rate, infection rate, transmission rate. Beta is the chance of getting infected. So the incidence rate, sort of, it's a small incidence rate, keep in mind. And this is how to simulate it. And here I plot each of the, so I have 260 64 suspicious people, 0.12, so very little infected, very little dead, and C, what was C? I don't remember. The last one, which is 65. These are the initial conditions. And look at the simulations. Simulations if you do not do anything. This is gruesome. Listen to me. This is gruesome. Okay. So if you do nothing in 15,000 days, if you do nothing forever, you don't do absolutely anything. Okay. So the equilibrium point where this system goes is 0 susceptible, 0 infected, 0 exposed, and almost everybody dead. You see, almost everybody dead. So this is a bit weird, I would say. This is a bit weird. Okay, maybe you can play with these figures and tell me that things are different. Things are different. Okay, but I don't know. I honestly don't know. This is interesting in any case, and in this is research. This is a research master, so this is research. Okay, this is research. Okay, essentially in these plots you do not do anything. Okay, so in some span of time everything is over. So actually everybody dies after 5,000 days. You do not need to wait for 15,000 units of time for this to happen, I'm afraid. Okay. Right. So I don't know. Contradict me somehow, but I don't know how that's possible. Of course, you can change here a lot of parameters. So you can, I'm not sure if you decrease this alpha guy, what happens. Per capita infectious rate. Okay, this is very low. Death rate is very low, as you can see here. So, I don't know, let's try again. Well, it's pretty much the same. Okay, it's pretty much the same. Not much is changing. Not much. What should I change more? Because these are very low numbers. What should I change? That I changed the transmission rate. I made it very small. Let's decrease this even more. Okay, because if I increase the incidence, things are probably going to look pretty bad. You agree?
Yes.
So it's only slower, but still everybody dies. So it's the same thing. Everybody dies. Come on, people. So go get vaccinated, for Christ's sake. I mean, even this stupid simple model shows you that everybody dies if these things happen like this. Oh my God. I'm not going to look at this any longer because I'm going to get depressed. I'm kidding, of course, but you see, I think you understand my point. Right. So this is pretty much it for today, I would say. I think it's a lot of information to process. Would you agree? Or wouldn't you agree, actually? Where was I? Yeah. Would you agree there is a lot of information? I think you can go through the lectures. You have all the lectures here prepared for you. So you can look in advance if you like. We have to wait for a little bit, and next week you can start after we finish the class next week. I open the assignment, and you can start trying to provide a solution to this assignment. Okay. Try to look in the book of Khalil as well. This is the mother Bible of nonlinear systems. It's a wonderful book. I totally recommend you people go through this book, browse this book, and check out the examples. There is a lot of exercises there, and there is the Chinese manual of solutions. Maybe that can help. Okay, maybe that can help. Right. From my side, there isn't much to say. So if you have any questions, comments, remarks, and so on, please please do that.
So far, everything looks very interesting.
Yeah, it's interesting, but you see, next time we are going to dive into math stuff. So you have to remember eigenvalues, you have to remember functions, you have to remember calculus. You see, but it's interesting. Yeah, I agree. It's a very large field. It's a difficult field. People didn't get through it very well, in the sense that problems are not solved completely. Of course, there are better and better algorithms, control algorithms, trying to mimic what's going on in the linear world, which is a complete world. So the linear control theory, if you ask me, I'm a fundamental researcher. I like researching concepts, basic equations, and stuff like that. So if you ask me, my opinion is that linear control theory is finished, is over. There is no new concept, I mean fundamental concept, like PID or Kalman or something like that, or output regulation, or estimation, or state detection. These are fundamental concepts. What people do nowadays, they only play with these concepts. But there is no new, maybe this data-driven control brings a new approach, brings a new face to linear control theory. But linear control theory is finished. There is nothing fancy to find in linear control theory. But nonlinear control theory is still an open world. So there is still a lot of things to be done. There are many concepts. There is wonderful theory, geometric theory, calculus-based, so mathematical analysis theory, systems theory, and so on, what we study here, what we try to talk about. But it's not enough, because the numerical part is very, very limited. Right? So my advice is go through the slides, because you have all the slides here, and I don't know, see if it's interesting for you or not. But I have to warn you that this is a lecture with a lot of math. We have to study that math theory. I'm trying to make it simple for you, but you cannot escape that. We can't escape that if we try to understand some nonlinear concepts. Okay, I used to work quite a lot in the nonlinear field in model order reduction. I had some nice results, I agree. Not numerically, of course, but analytic and fundamental. But well, that's a different story. Anything else, please? I mean, this is a master class, so we can discuss anything. Feel free to open the subject and let's try to discuss related to the subject, or tangent to the subject, or not related, or whatever. If you have anything you would like to talk about in these minutes, please feel free to do so.
Do you have a recommendation for a book which sums up all the math things we're going to need?
I told you. Let me show you once again. The book of Khalil, I just told you. This is the Bible of all Bibles of nonlinear theory. This guy. Khalil, Nonlinear Systems, 3rd edition.
Okay, so they also give a good introduction to that, I think.
Yeah. This is the best introduction you can get, because this contains all the nonlinear concepts used nowadays. Although the book was written in the 60s, 70s, or 80s, or I don't know what, 90s or so, it's still fundamental. There is no new stuff built up for nonlinear systems. This is the best we can get. So I'm going to try to open it for you. Okay, so this is Prentice Hall, Nonlinear Systems, 3rd edition. You see? Okay. Yes. Look, contents. Okay, pendulum, tunnel, diode circuit, mass spring. So this is the oscillator. Yeah. This is the mechanical oscillator. Artificial neural network. Look, adaptive. So you can see, look, you have examples, you have exercises, then You talk about second order systems. We are going to talk about as well, because our class is structured based on this book. It's a huge book. Can you see? So you have a lot of, it covers everything. Covers everything. Okay. Agree? It does.
Yeah, of course.
Does this answer your question? So if you're able to read this book, trust me, there is not much else you need for the time being.
Okay, then I will stick to that recommendation.
Okay, you can also find other books. There's books of nonlinear systems and chaos. So there's other books as well. You don't have to stick to this, but I recommend to start with this book. At least to start, okay? All right. I have also another book of nonlinear control systems of Van der Schaft and Nijmeijer from the Netherlands, but that's so difficult, it's very hard to go through it. And there's also the book of nonlinear control theory, which is more industry-oriented, but also very fundamental, of Alberto Isidori, Italian, nonlinear control systems. Try to look that up as well, and see if you can understand anything from that book.
Okay.
Hey, Alberto, sorry?
Okay, I will do that.
Yeah, Alberto Isidori is the author. Look it up. It's also a fundamental book in nonlinear control theory. Okay. Right. Anything else, please? Anything else, please?
Not from my side, I'm fine.
Okay. The others? The rest of you? Anything else?
For me, everything is fine.
Okay. Andrei?
For me either.
Right. Well, thank you very much for being here today. I'll see you next week. Enjoy.
Thank you. Bye.
Thank you. Bye.
Bye.
Thank you. Goodbye.
Cheers. Thanks. Bye.